So let's say we have three vectors u, v, and w, such that they're in this arrangement, where v and w kind of share a vertex at the pole or at the origin, however you want to think about that location, and u goes between their terminal points. That is, v and w start at the same place, where for simplicity we have it be right at the middle, and u goes between their ends. Well, if we want to talk about what happens to the angle between v and w, the first thing we can do is just take some quick thoughts about what that triangle type shape that we're forming actually looks like, where we don't know anything about really anything in there except maybe what those vectors are. So we can use the law of cosines to say something about the lengths and that angle. That is, we have the magnitude of u squared is equal to the magnitude of v squared plus the magnitude of w squared minus 2 times the magnitude of v times the magnitude of w times cosine of that angle. Okay, that's quite a mess. But from here, we can think about what those magnitudes look like in terms of the points that we go from, where we're going from the origin to some a1, b1 for v and some a2, b2 for w. So if we want to talk about what's going on here, we will have that on the left side, we are going from a1, b1 to a2, b2. So the magnitude of u will have form a1 squared, oh, excuse me, not a1 squared, I'm getting ahead of myself. It will have form a1 minus a2 squared. That is, we'll get that for its horizontal movement, plus b1 minus b2 squared. Great, we've made it messier, but we don't have as many magnitudes. And on the right side, well, those are actually even cleaner, because the horizontal components of each will be determined by a1 and a2, and the vertical components will be determined by b1 and b2. That is, for the magnitude of v, we'll have a1 squared plus b1 squared, while the magnitude of w will get form a2 squared, which is just horrible looking, not least of which because I have managed to fill in the a, so it just looks like a blob. But we will have a2 squared plus b2 squared, and then to save space and a bit of sanity with a's and b's, we're just going to leave this term in terms of v and w. So we'll have minus 2 times the magnitude of v times the magnitude of w cosine of theta. And then from here, things get a little bit messier. There's a bit of work with multiplying out what happens in those a1, a2s and b1, b2s. I'm not going to write it down here. You can check it for yourself, or really what you should do is multiply it out yourself and see that this happens. But if we take those terms and then expand them, bring out some of these, you should tell a1s will cancel, b1s will cancel, a2s will cancel, b2s will cancel, and we'll just be left with those doubled type of terms, where what we'll have is a minus 2 a1 a2 minus 2 b1 b2, where that's going to be equal to minus 2 magnitude of v magnitude of w cosine of that angle that we're trying to deal with. And then from here, we've got minus 2, minus 2. You can just get rid of those minus 2s, divide the whole thing through by that, and what we'll have is a1, a2 plus b1, b2 is equal to the magnitude of v times the magnitude of w times cosine of theta. Yeah, by itself, not great, but this, if we think back to our last bit, we should remember, is the formula for the dot product of v and w. So, we have that v dot w is equal to the magnitude of v times the magnitude of w times cosine of the angle between them. That's nice. It's a different way to get to our dot product, but for our purposes here, we're usually going to be in a situation where getting the dot product is easier than getting that angle. And in particular, if we want to turn this around and get our angle theta, we can divide over those magnitudes and take an inverse function, where we would say that theta is equal to inverse cosine of the dot product, v and w, divided by the product of their magnitudes. This is how we can find our angle between two vectors in terms of their magnitude and their dot product. And to understand this, we're going to look at an example. So for this example, we want to find the angle theta between vectors v equals 3i minus 2j and w equals minus I plus 4j, where we have them graphed like so. So for this example, what we're going to need to do is just find the pieces we need to plug them into that formula. In this case, we can start by finding those magnitudes. For the magnitude of v, it's something we've done before, it's pretty straightforward. We have 3 squared for the horizontal component, plus a negative 2 squared for the vertical. And you take that, you get 9 plus 4, or the square root of 13, which is the absolute best you can write for that because 13 is a prime number anyway. Meanwhile, for w, if you want to get that magnitude, it's really the same idea, just different numbers. There, since we have a negative I, our horizontal is going to be a negative 1 squared, while our vertical will come from 4. We'll get 4 squared. Negative 1 squared is 1, 4 squared is 16, so we're going to get another prime number under radical, this one root 17. And then we need our dot product. That v dot w will take form here. 3 times negative 1 plus negative 2 times 4, or if you prefer, and most would, negative 11. And once we have all of these pieces, we can then put them into our formula, where we would get that theta is equal to inverse cosine of this value here for the dot product, negative 11, over the square root of 13 times the square root of 17. It's quite an ugly number, and as a result, we're going to get quite an ugly degree value here. That is, we're going to get quite an ugly angle coming around there. We do have to be careful about what the cosine function does here, but we should get an angle of 137.7 degrees between those two vectors. And from here, we're going to talk about some important natural relationships that come from certain types of angles between vectors. In particular, we're going to talk about what happens when we have an angle between vectors of 0 or 180 degrees, or when we have an angle between them of 90 degrees. We have special terminology for that. We would call our vectors parallel or orthogonal, but that's what we'll see next.